Hi, so welcome to the final BunG seminar talk this quarter. It's a pleasure to introduce Aaron, who will be speaking on a mosaic of examples and basic properties of BunG.
Thank you so much to the organizers for inviting me. Yes, very sorry, Sasha Balinson won't be here, but he'll be there first next quarter. So this will be very exciting. We'll start off with the bang. All right. My job is to sort of rant about BunG. And specifically, I wanted to give some very concrete examples. We've had a lot of theoretical talks describing these sort of high-level structures. And you can get a good sense of quite a lot of them from just the example of BunGL2 P1. So I thought I would actually go back even further a little bit and begin with the old story of vector bundles. Can you see this? It's all good it's within the range of the camera. Perfect. Vector bundles on P1.
But this is more of a rave than a rant.
This is more of a absolutely, yes. So actually, in this case, this works over an arbitrary base field. And we're going to give a very, very basic linear algebra argument for the theorem that Grothendieck proves. And it will actually be very similar to the proof Grothendieck proves. We'll compare the two. That every vector bundle over P1 splits into a direct sum of line bundles. But there's a completely non-technical proof that does nothing but linear algebra. And it's actually kind of a nice linear algebra theorem. It's the first time you see double coset decompositions of the kind that we saw with Mintom's talk. Maybe a little less difficult than those. But okay, so let K be an arbitrary field. Maybe later we'll have to make it algebraically closed. All right, so write P1 as the union of spec KT and spec KT inverse over GM, so spec ring of Laurent polynomials. And let E be a vector bundle over one. So we know already of old that a vector bundle is the same thing as a GLN torsor. So what we're going to be working towards is classifying the K points and understanding the sort of geometry just at the level of the very basic K points of the stack BunGLN. Hoping to understand BunGLN P1. All right, so squeeze in a little bit more space here. Let's start with a very, very elementary lemma. That if we restrict E, the vector bundle, to spec KT, the sort of upper open set or the positive open set, this is free, or it's a trivial vector bundle. The proof of this is just the classification of modules over a PID. It's a quasi-coherent sheaf over a PID. Therefore, it will split up into a torsion and a non-torsion part. And in particular, if there is any torsion, E will have torsion, so it must be free. It must be torsion free, which implies it must be free, which implies that it is trivial. So classification of PID, I said it, but won't write it down because my handwriting is much slower than my statement, and this is certainly not the most interesting part of what I'm hoping to get to. Classification of PID. The punchline being that KT is a PID. All right. So for this reason, we can always trivialize E on the upper and on the lower. So E restricted to spec KT is going to be isomorphic to KT. So I guess I've chosen M. Let M be the rank of E. And I should mention that this proof that I'm about to give, this interpretation is a very elementary linear algebraic way of dealing with things, comes from Hazer-Winkel And there's one other author whose name I can't immediately find. And what's one more? This is embarrassing that I haven't written down. I should have written up references more carefully, but yes, it's a nice sort of 3-page, very elementary argument. So this is trivialized in this way. You can also restrict it on the other negative open set. And it's, of course, isomorphic to KT inverse in the end. And we can always then restrict it to restrict these. And we're going to have to construct, so this is now restricted to the overlap of the two sets, the GM. And we're going to have to construct an identification from the one vector bundle to the other. So let's call this map phi. Phi will determine the sort of gluing of this vector bundle. Since there's only 2 open sets, we don't have any higher gluing conditions. So any such phi in the element in GL2 KT inverse will give rise to a vector bundle. Now, I don't know if you can see this from this bottom right here, vector bundle E. And vice versa, any bundle E, you'll be able to find such a glue. They do this cleverly by dividing the board in 2 like this. All right. But, did I? Oh, yes, sorry. We'll get to GL2 eventually, but this is GLM. Thank you very much, Professor Lucy. Yes, this is GLM. So, yes. And now, of course, there were some choices that we made here. In particular, there was a choice of trivialization of identification here, and a choice of identification of the trivialization here. So to get the data out correctly, it's a double quotient. So if I want, phi, so what am I saying? I'm saying that in fact, the exact bijection is GL2 K TT inverse modulo. Well, problem of writing a double quotient when you haven't given yourself enough space. Now, this is actually very important which side I get, which side I do, because I've got to consistently use consistently the one side versus the other. GL2 A. Each time. Okay. Thank you so much. Feel free to call out every time that error appears here. So this double quotient will correspond set theoretically to vector bundles. So already we see an example of a double quotient, which is very similar to what Min Tom wrote down last time. The difference between this double quotient, this is an aside. Min Tom's uniformization, so the 1-point uniformization, glued in a formal neighborhood. So this will actually be GL2 K T mod, again, M, mod GLM K hard brackets T, mod GLM. And this is exactly the same because when you restrict, this comes from the curve, it comes from restricting the functions that are defined away from the puncture to the puncture disk, which is given by the Laurent value GLMs. And so you can see that there's a natural map from this guy to this guy, and it's a kind of a question?
Yeah, should that be just a T instead of a T first on that right quotient?
Yes, it should. Wow, sloppy error. All right, yes, it should absolutely be. Thank you so much. And you can see that there's a map from this guy to this guy. Thanks so much for pointing that out. But it's the point is that actually the inverse map involves a kind of approximation theorem. So in general, when you're dealing with the kinds of groups, you'll see some sort of various kinds of approximations occur. So anyway, this is now a linear algebra problem. What we want is a canonical form for this double quotient, for that at the, I won't write it again for fear of writing 2 as opposed to m and we're getting an inverse double quotient. And so this is now not such a difficult thing, and so the claim, any such class in this double quotient is to the diagonal matrix given by t to the r1 and t to the rm where we may assume, you can always use a permutation matrix to sort of reorder these. So you assume R1 is greater than or equal to, so on and so forth is equal to greater than or equal to Rm. And the Ri's are in Z, of course. They are certainly not necessarily positive. So, okay, let's do so there are two, and this representative is unique. Right. So let's begin the proof. Uniqueness. This is the most annoying part of the oh sorry, question. This is the most annoying part of the talk. I think actually I'll probably just skip it for the nonce. Uniqueness follows by actually examining minors of the matrix. And let's see what time we're at. Oh, actually, it's only 15. Okay, I thought it would be examining the minors of the matrix. Yeah, okay. So, okay, we might as well, for completeness' sake, go through this. So, okay, so let A I1 through IK, J1 through JK, for I1 less than IK and J1 less than JK, denote the K by K minor with row indices, rows I, L, columns JL. Just by the general theory of block matrix multiplications, if we have AB product and we want to take its minor, it's always true that this is going to be the sum over all indices R1 to RK. I guess one interesting point about this actually is if you read Lomon's paper so why am I belaboring this point? If you read Lomon's paper, which is on geometric Eisenstein series, you'll see that this kind of computation regarding these indices actually shows up automatically. You will actually somehow not be able to escape it, at least when you're dealing with this in the elementary way. So this is actually something that you will encounter sort of in big boy mathematics. And I was sort of interested that it seemed to all sort of come from this very basic computation here. This is the OG appearance of these sorts of computations. So when Lomon computes some, I guess it's some supports or something like that, he does a very similar computation to this.
Hang on, is this an analogy between the computations happening here, or is the computation actually come from this geometry?
I think actually it may be coming from the geometry. I need to put some more thought into it. What I will say is that this proof that I'm about to go through is actually, upon analysis, identical to Grothendieck's proof. And I want to give a little comparison between the two again, because I think it's actually it's illustrative about the structure of BunG in this case. This is actually Grothendieck's proof, although you would not, you would not be caught dead seeing indices. I don't know, Professor Lucy, maybe you would think that this is definitely not true to the spirit of Grothendieck's proof, but it is actually, if you analyze the two and compare them, you'll see the same techniques are appearing. So yes, and indeed these kinds of computations. So also very similar to what Professor No was writing down on the board. And again, I haven't really thought about the extent to which that's actually on the nose an analogy, but it certainly looks a great deal like it. So okay, so all right, now say A T inverse is just an arbitrary guy in GLM, pay T inverse. Then and write D R1 Rm for the diagonal matrix. Then we have assume, we're going to prove uniqueness, so assume D R1 through Rm is equal to D R1 prime through Rm prime, is equivalent to, sorry, not equal to. Then obviously there exists V and U, such that B inverse D R1 to Rm equals D R1 Rm prime UT. So V is a matrix whose entries purely have T inverses, and U is a matrix whose entries purely have positive values of T. Then and again, this is the last bit of coordinates we'll have to see. V1 to dot dot to K, I1 to IN T inverse times when you take the the IJ minor of this one, this just becomes T RI1 plus dot 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 plus RIM is equal to T to the R1 prime plus dot 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 plus RK prime U I1 IK 1 to K T. All right, now clearly there exists some indices such that U I1 IK 1 to K is not equal to 0. If that were not true anywhere, that would just be a complete block of zeros, and we know that that's not the case. So what we see here is because this only involves T's, this will up the degrees of the T's. This only involves T inverses, this will lower the degrees of T's. For this to be equal, we actually see that for this particular index, assuming they're not actually 0 on the nose, we see that R1 prime plus RK prime is less than or equal to R1 plus RK for all K. All right, and now comes the one little inside of the proof. This implies R1, is less than RI1, is less than RIK. And because we've assumed these to be in decreasing order, this is in turn less than or equal to R1 plus RK. Okay, so this is the last bit of these sort of awful matrix computation coming here. Now we just notice that this is entirely symmetric. I can hit this guy with the inverse matrix, and this guy with the inverse matrix, this guy with the inverse matrix, and I end up with dr1 to rm, ut inverse is dr1 prime rm prime ut. And what does this, that's probably ut inverse, that's bt inverse, sorry, bt inverse inverse. And this implies the inequalities work in exactly the opposite way, which means that R1 plus dot plus RK less than or equal to R1 so that's K. And yes, and those two are inverse, so therefore there must be equal. So what's actually going on here is we are sort of restricting to subbundles and taking volume forms. We're sort of taking kind of determinants on each component of these sorts of minors. And so this is another trick one sees a lot. So, okay, so now comes the more interesting side, which is that this canonical form always exists. And this is where you see the direct comparison between it and what sort of Grothendieck does. So, okay, so now we will show existence. All right, so it's in Dr. Monahan. So firstly, if m equals 1, this is actually very trivial, although as an algebra problem, but it's not so trivial as a algebraic geometry problem. If you think about it for a second, this is telling us that pick of an elliptic curve is discrete, it's just z. And that's actually not, immediately clear. Oh, sorry, pick zero of an elliptic curve is the point, and the entire, I'm sorry, what am I saying? Pick of P1. Sorry, what am I saying? I thought you said pick one and correcting. It's like, no, the degree ones don't form a group. Sorry, yes. Pick of P1 is pick. This is what makes this so nice actually as an example, is that pick is trivial. So pick of P1 is trivial. So but if m equals 1, this is just going to be KT T inverse TL1, which is the same thing as a pick like in units. This is going to be KT star mod K inverse star. And the units are all powers of integral powers of t in here. The only units in there are multiples of k, so we can always reduce this to something. All right. So now saying there exists such a representative for in the double quotient for all m minus 1 by m minus 1 matrices. And say we're given some A T inverse inside of GLM K T inverse. So first things first, if we're given such a thing, we examine the first row, call it A11 through A1M. We examine the first row. We can use, so what am I allowed to do? I'm allowed to do column operations with positive powers of t, and I'm allowed to do column operations with positive powers of t, and row operations with negative powers of t. So that's the sort of rules of the game in rejiggering this matrix in this interesting way. So the first thing we can do, and if you've done Ginsburg's Algebra 1 class, you'll be very familiar, is you can find the GCD of the first row, and you can kill everything else off. So we can reduce by simply multiplying on the right by something to something in the form B11 0 and then something else down here, garbage down here that we can know how to deal with. All right, so that's the first thing. That should make it clear that is not another 0. That's a B11. So that's the first reduction. Then the second reduction is to imply, or the second reduction is to utilize our inductive hypothesis. So, so we now have B1, 1, 0, dot, 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 0, and then other stuff. Well, this matrix on the inside we can deal with entirely independently, and so we can reduce it to something of the form. Well, okay, I should just make a slight side comment. B11 now is going to be a factor of the determinant. So I could mention when we're dealing with a matrix in where's my double quotient? Where is my double quotient? There it is. When we're dealing with a matrix in this double quotient, clearly it's going to have to be invertible, which means it's determined it's going to have to be a unit in here. So its unit's going to be a scalar times the power of t, basically. And so we know, just up to moving things around by scalars, we can assume it is just the power of t. And so if B1 divides this, it itself must be a power of t. So we're going to write this as t to the k1, and then we have t to the k2, dot, 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 down to t to the km. And then this is all 0 up here, and then this is going to be c2 dot, dot, dot up to cm, and there's zeros in here. So this is applying the inductive hypothesis and observing that B11 must be a power of t. So far, so good. Now the game is we're going to have to kill C1 through Cm. So first things first, what can we automatically kill? I'll push this out. So observe that if we take our matrix TK1, TK2, C2 dot 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 to TKM, CM 0, 0, 0. And I multiply it, I'm allowed on this side to multiply it with positive. Now if I multiply it by unipotent, say just look at the C2 term here, I can basically if any term of this, if any monomial of C2 is less than K2, I can kill it off by bumping it up by a monomial here, let me see if I'm getting this right. I can bump it off by this is what is greater than T2, and this is a K2. Right? So if anything's greater than K2, I can bump it off by basically taking K2, increasing its power to whatever it is, and then subtracting it off here through an element. So I can kill any term that's greater than K2. I can similarly kill off on the left, we can kill off any term with degree less than K1. Less than K2. So we can assume that these are sort of monomials that are purely, and I think I did invert these. Kill off any terms that are bigger. I can kill off any terms that are, I can kill off any terms that are less and terms that are bigger. One has to be a little bit careful to make sure that one isn't talking nonsense, as one can get very confused in this. But yeah, so one can basically bound the degrees of each monomial inside the CIs. And what we're going to show is that actually we can force K1 to be big enough so that it's bigger than the other Ki's, that there's just no monomials possible for the Ci's. And this is exactly what Grothendieck does in his paper in constructing a kind of destabilizing bundle. So here comes the actual thinking of the theorem here, as opposed to sort of just as I say, this is incredibly elementary, and maybe even dogmatically so. Maybe it's too much, but it's kind of fun to see some things that are like really not so that actually do underlie this discipline, but are at the level of polynomials. So okay, so yes, so we can kill off the term. So consider all matrices equivalent under our notion of equivalence as, well, I said above, it was what was just erased, and above to A that's right, A to T inverse. And of the form all right. Now, there's one other thing that we're going to do. Without loss of generality, let's bump up all the powers so that everything's positive. Assume that everything's in KT. We could have done that at the very outset by just multiplying everything by a single power of t's. That there was no negative powers in our polynomial, in our polynomial. So we can assume that all these are actually in the polynomial ring, and they have the bounds of the kinds of degrees that we were talking about. Yes. All right. First things first, we note that when we made that reduction, the K1, Ki's are all positive numbers, and their sum is the degree of E, our original, is the determinant of our original matrix. So let's write this det A T plus some constant. Whatever that constant we use to shift everything up was. But the point is that these are bounded below by 0 now and above by some numbers. There is actually a maximal K1 that we can find here. And that maximal K1 that we find, is going to, I claim, be bigger than all the other Ki's that you see in this blue. So choose K1 to be maximal. To be maximal, and we know that that maximal will be achieved because these are not bounded above. So again, in Grothendieck's paper, you'll see he says find a line subbundle of E whose degree is maximal, and this is exactly what he's doing. He's constructing a destabilizing bundle, and that's how we're seeing it in this sort of framework here. So claim K1 is greater than I guess when we perform the reduction here, we can assume that K2 is greater than or equal to Km because of the inductive hypothesis. So K1 is greater than K2. And the way to see this is a kind of SL2 computation. If it weren't, it would not be if K2 were bigger than K1, it would not be maximal. So the way to see this is, say we had some matrix, and we're just going to look at the upper right-hand corner here. xk1, xk2, where in this case k1 is less than k2, so it's not bigger. And then we have some C, and C is going to equal to, A1 x to the K1 plus 1 plus, you can kill off all the other terms, whatever this index is, K, K2 minus 1. The first thing we can do is we can apply a kind of biovector element. 0, 1, 1, 0. This we can apply on either side. It doesn't matter. This is in case. It makes no difference. You may close that door if music gets too bad. Oh. Thanks so much, Nikolai. Thanks so much. This is C x to the K2. X to the K1 and 0. Now that we have K2 on the upper row, we can repeat this argument. If K2 is bigger than K1, then we can kill off this term here, replace this row with one for which K2 exists here, and this is 0. But that means that I can basically rewrite this matrix with something in the upper right corner, where this is then equivalent to x to the K2 times something down here. Where my upper right corner has an exponent, my upper left corner has an exponent that's bigger. So this is exactly, as I say, the linear algebra view of what Grothendieck said. So that's a contradiction. And apologies if this is a completely laboring point. I urge you to take a look at Haswinkel and his everyone's name's paper if you're confused about any of the linear algebra here. But it contradicts maximality. So once we know that K1, K2, that K1 is actually can be assumed to be bigger than K2, and therefore all these other ones, then there just are no possible monomials for the CIs. You can kill them all off. So again, the way that part of the argument is seen in Grothendieck's paper is as a kind of fun little cohomology argument. And let's see what time we're at now. So 4:39. So yes, so I think my original plan was to actually go through, outline Grothendieck's argument, and compare it to this one. But since that's probably broadly known, in some case you'll probably find it out, I'll skip that. And before the break, which will occur in 10 minutes, we'll try to get right to the heart and soul of the issue of what I want to talk about today, which is what this actually tells us about what BunG L2 E1 looks like. Okay, so all this was kind of a practice of sort of perspective of why you can do everything, how you can do everything just completely pig-headedly, sort of in a very easy way. So let's So as I say, I do urge you to take a look and compare Grothendieck's cohomological argument with this, and you'll see that they are actually pretty much identical. Though one is certainly slicker, but it is fun that you can sort of do everything in this extremely explicit, brutally explicit way with just matrices. And it's kind of also a fun little matrix algebra problem. It's almost like a competition problem of being able to row manipulate with positives and column manipulate with negatives, and asking what you can get from that. So, okay. So the next point for us is, what does BunG L2 E1 look like? All right. So first things first, the determinant of these matrices, aka is also known as the degree of the vector bundle. So that actually separates the component, the stack, into an infinite class of disconnected components. So degree of vector bundle gives all connected components. This is very groovy. I feel very yeah, see, usually when the audience is terribly irritated by these, but when you're up here speaking, you can feel like you got it. This is amazing. Okay. So that's the first thing. So there's going to be a z's worth of disconnected components. But if you notice, the combinatorial data, you might think that because the vector bundles themselves, and then obviously each isomorphism class a vector bundle, is isomorphic to OD1 plus OD2 for some integers D1 and D2. So somehow there's, you might think that because this is an entirely discrete set of data to describe P1, you might think that there's no geometry whatsoever, it's all discrete. But you can see that the connected components, there's only a z's worth, sort of z squared's worth of disconnected components. And so here's what's going on. I think I actually have colored chalk, but I didn't bring it out in a particular manner. This sake. Wow, it's so like resonant too, isn't it? Yes. All right. So, what does the actual stack itself look like? You'll have a point, and then you'll have a sort of, which is a big open point. And it will specialize to another point, and this will specialize to another point, and this will specialize to another point, in these sort of open strings, a bit like Russian dogs. And this point right here is the one corresponding to, say, O plus O. This one right here corresponds to O1 plus O minus 1. This one right here corresponds to O2 plus O minus 2, and so on and so forth. These all have the same degree, in this case 0. And the next one will have degree 1. There is a sort of starting point, the big cell inside of this, O1 plus O. This will then specialize to O2 plus O minus 1. And then this one will specialize plus O minus 1, specialize to O1 plus O minus 2. So again, by the way, I guess I should mention that you can see from this big computation already, you can actually use this as a definition. I think the way that I had written out the double quotient, the single matrix in this double quotient given by K to the R correspond to O minus R. Unfortunately, because I put the minus on this side, but one can always check on so when one's dealing with this, every vector bundle splits into a sum of line bundles, and we have the data for it. But we see that this is sort of what the stack will look like at the level of just k points. This is in some sense the coarse moduli space. This is not being technically correct at all. The coarse moduli space would just be these points. This is just the k points of the stack of BunG. And so you have this sort of infinite class of them. You have it going both ways. And each one sort of specializes in this interesting way. So what I've shown you so far is that this data corresponds to everything. What I need to convince you of is that somehow this is in the closure of this. And this is in the closure of this. And this comes from Ramanathan's theory of deformations of principal G-torsors on but let me just see how I've ordered it in my notes. Please. Yes. The other point about a stack, of course, is there are automorphisms. And we haven't listed the automorphisms here. So the automorphisms, as we know, from I guess it was probably Ginsburg or Nick's talk, at the level of vector bundles correspond to the actual automorphisms of the G-torsors. There are other there are non-isomorphism maps of vector bundles which don't correspond to anything at the level of G-torsors, but you can certainly recover the automorphisms of this one. So this one right here, for instance, is going to be the automorphisms of O plus O as a vector bundle, which is simply GL2K. So actually, maybe let's this one right here is the automorphism. This is a vector bundle. Well, this is a bit complicated. It's a sort of extension. There's two GMs coming from this, and there's however many HOMs there are from O minus 1 to O1. And that's a GA3. So it's going to be EM squared, and I think PA cubed. Next term will be GM GA. I should make this really subscript is GA to the 5 n squared, and so on and so forth. So this is the example, the sort of level of this stratum here, of this connected component here, when we examine the actual isomorphisms, the automorphisms of each one. So if you were to think of it as a disjoint union of stacking points, it would be point mod GL2K, point mod this group, et cetera, et cetera, et cetera. And something to notice here is that the automorphisms, as you become more specialized, become more simple. They become more abelian. This GA begins to dominate. I asked Professor Valenson if this was a general phenomenon. He said yes. And in fact, an example where you see this in a completely different context is in physics. If you have the Galileo group, if you have the Lorentz group, which is the symmetries of special relativity, and you let C, the parameter of the speed of light, go to infinity, you end up with I think a semi-simple group to turning into a semi-direct product in this way too. So you can see this is the kind of general fact about deformations that they become as you become more special, more simple in this way. All right.
What are the automorphisms for the other?
But then come on. So there are these. They actually look essentially the same. Every other one. There's sort of two periodicities. This one right here, of course, is not. This one's also going to be a semi-direct product because again, kind of computed. It's ought, O1 plus O to O1 plus O. You can sort of think of this as a kind of 4x4 matrix where you're allowing entries to be homogeneous polynomials. These two communicate one of these two. There's no map from O1 to O, and there is a map from O to the 1. So these are all still kind of parabolic in some sense. The other point is, if you remember Griffin's talk, he was talking about the Harder-Narasimha stratification. You can see these sort of canonical parabolics emerge in the groups in a really clear way here. Cells, the whole lot of things. So you can start to see the kind of, I mean, in this case, I think the data actually just descends to all the different K points themselves when they're sort of strata in this way. I'm not 100% sure of that, but it seems to be what I heard. But yes, you can start to see from this the Harder-Narasimha type stratification. So let's just quickly check time. 4:49. So I think with this, having belabored a really nice theorem of Grothendieck can turn into a really horrifying theorem in linear algebra, and having drawn a picture, I think we can take a break for 10 minutes and resume, and then I'll next speak about the B reductions and T reductions in the case of GL2, where you start to see some basic sort of very baby geometric languages here. So that's what I hope to do after we return. Thanks so much.
So let's come back.
Absolutely. So last time I gave a very difficult and fraught proof of what BunGLN of P1 looks like combinatorially, at least at the level of K points. And now I've described sort of automorphisms in the strata, again, very explicitly. One slight point that I think deserves mention here is that the affine Grassmannian, which is K T, sorry, it's actually soft T, GL2 soft T, mod GL2 hard T. If you remember from Professor No's talk, this is an MC, and this is constructed out of taking inclusions of closed subsets. In this case, this is constructed the moment you add that second quotient on this side, which is K T inverse, you sort of change the dynamics of quite substantially. And now everything here is a sort of union of opens. Each one's open in the next. So this is actually sort of inverts the whole process. So BunG looks quite different from the affine Grassmannian in this way when you take that extra quotient. So, let's go over here. And, yes, I guess another point is, and one can do this, one can now actually compute the mass of these stacks very explicitly. In fact, so I did in my notes, I posted later. The point is that if this were over a finite field Q, these would each count for this would count for 1 divided by the order of GL2 at Q. This would count for 1 over the order of this group, so on and so forth. So you can actually explicitly compute for, and this is only one component of a BunG GL2, let's say semi-simple, you could compute so-called Kamigawa number this way. And this is the mass of BunG. And it turns out it was a very big theorem due to Gates and Lurie that you can write it in a way just in terms of properties that are X and kind of fibration of EG over X, its mass. It's a very nice result and generalizes or is an analogy with the classic Weil-Siegel mass formula. So it's a very, again, if you actually want to see some baby examples of those kinds of computations, level of BunG, so you can do so explicitly. So, okay. So we're going to now study this basic diagram. Let's see JM minus GM. We're going to assume everything's over an algebraically closed field now, mapping into GL2, which is G as diagonal matrices. We're going to let B be the upper triangular matrices. And we're going to consider the diagram. I'm going to label this Q and P. So this diagram, you have B surjecting by modding out by the unipotent subgroup onto the torus, B mapping into G. So this is the basic diagram for so-called geometric Eisenstein series. And in general, for Eisenstein series, if you're familiar with the classical automorphic world, you have a Delic double quotients over each of these. And we know from Lynn's talk that Delic double quotients correspond to take the BunG, the stacked BunG. And so in general, you can sort of you can take either functions or more generally sheaves, and you can pull them along T and push them along, pull them along Q and push them along T to get functors from sheaves on BunG T to sheaves on BunG, which are the analogs of induction functors and the analogs from automorphic form theory and the analogs of Eisenstein strings. So we're not going to be doing any sheaves, certainly not pure base sheaves in this talk. That'll be next quarter. We'll be discussing sheaves and stacks in great detail, and D modules in particular. But I do want to describe the geometry of this in the case that we have access to it, because the geometry is very, very interesting. So this gives rise to the stack BunG P1 to BunG T P1 to BunG 1 Q. And we'd like to study the fibers of these maps very explicitly, using only not as bad matrix work as we had in the first part, but using some matrix work to make it at least the talk have some vested coherence. So now BunG T is just BunG GM times GM. So what does BunG GM categorize? It categorizes line bundles. So BunG T E1, I can give general S point here, equals a pair of line bundles order pair of line bundles over S times P1. BunG is a little bit more complicated, but one can see by essentially the same associated bundle construction by taking the by taking the standard representation of B as given by 2 by 2 matrices and by taking its action on the column vector 1, 0, one can see that this actually corresponds to a pair L E, where EL is a line subbundle of E. Over S times V1. Locally, a direct summand. This is important. That means that E over L has no torsion. And BunG GL2, E1 S just equals, I'm sort of not aligned my work correctly on the board. Apologies for the terrible board space. If I had notability, I would circle this and push it down, but we're not in the virtual anymore. So this just equals a rank 2 vector bundle. Again, to be really technical, all of these are groupoids. This is the groupoid of pairs of this sort. This is the groupoid of pairs of this sort. And this is the groupoid of rank 2 vector bundles. And the maps are exactly what you would expect. L comma E will map to, well, it'll map to L comma E over L. Those are the two line bundles that we produce. And here it will just simply correspond to E. What we want to actually, in the cases where we have access to the K points, study the fibers of these two maps. And this is actually a very nice little homological algebra problem. So let's study K points. Let's assume S is spec K. So these just correspond to a line bundle over P1, a vector bundle over P1. And so let's study the maps Q and P. So.
Is there a double quotient description for BunG?
Yes, there is, and we're gonna. That's when the matrices will show up briefly. Yes, don't worry. That's coming. All right. So in this case, what we're going to do, we know how to characterize all pairs of line bundles. So fibers? Want to compute the fibers of Q. Okay, so let OD1 comma OD2. Yeah, that's more of a careful what you ask for kind of comment there, because there certainly is, and it's again very matrix oriented. OD1 comma OD2 be an element of BunG T1. Okay. All right, you want to know basically what the stacky fibers are of this map. So remember what stacky fibers means. They mean you actually look at the points that map to the corresponding points, but you look at the automorphisms that lie over the identity automorphisms. Now, this is actually kind of interesting because this is not a representable map, as it will turn out. But it's sort of half representable. Half the time it's representable, and half the time it's perfectly not representable. Which is to say that there will still be automorphisms that get mapped to identity here. And there's a sort of great something to these two regimes which are connected by Serre duality, basically. So this is a very nice little fact. So, okay, so first things first, how would I classify this? What do I need to produce? What are just the k points of BunG BP1 that I need to produce this? Well, I need to rank two vector bundle, of which this is a subbundle and this is the quotient. So this is obviously categorized by x of OD2, extensions of OD2 by OD1, which is, now we'll have our homology, H1 of OD2 minus D1. One tends to the inverse of the other, tends to the dual of the other, which is isomorphic to H0 O D1 minus D2 minus 2. Check. This is the dualizing sheet. This is O minus 2. And this has dimension equal to D minus D1 minus D2, which is, of course, or 0 if D1 minus D2 is less than 0. So it critically does depend on the order of the line bundles. If D1 is greater than or equal to D2, there'll be a nice space living over this, and it will actually, I claim it will actually be exactly this affine space given by this sort of X group here. But if D1 is less than D2, there's only going to be one point in the pre-image, and that's just going to be the trivial extension. But the trivial extension at that point will actually have automorphisms. And the automorphisms are going to be, look a bit like the space in the case where they're flipped. So there's some beautiful sort of duality going on here. But to implicate Nikolai's question very, very briefly, I really don't want to put you through quite a lot of matrix computation already, but just to see that it's.
I just make a comment.
Yeah,
I
absolutely.
don't know if you're gonna address this, but it's like you could really think about these fibers as like it really is like R gamma of that line bundle shifted by one. Like it's like the R, like you can view a two-term complex as a stack in a natural way, and it really is that vector stack.
Yeah, absolutely. Feel free to comment anything if you have higher level. This is just examples because we've entered and we're gonna next quarter it's gonna be even more highfalutin. But yes, so the way to think of this as double quotient is, of course, it's just going to be B K T T inverse mod B A T. Don't worry, I will not prove this. It's actually easier than proving, and this helps with an inverse to be consistent. B K T at the level of K points. This is actually correct. Gives you the K points of the stack. And in particular, what happens is basically T to the D1, T to the D2. Now you can do exactly what I suggested. Now, of course, this is going to be 0 because it's only B value once it's forced to be 0. The question is, what can I sort of reduce the stuff here? And again, column and row manipulations basically allow me to kill the things that are less than D2 and bigger than D1. Because I can increase the D1 to kill off a term here, and I can decrease the D2 on this side to kill off a term here. So this is going to look like A1 T to the D2 plus 1 plus plus A. So I think I got my indexes correct. D1 minus D2 T to the D1 minus 1. So this is going to be a polynomial, and of course, the polynomial's coefficients are what we're actually asking for here, or what things that will vary and give us the different points. And actually, how many of them are there? Well, there are the numbers non-inclusive between D1 and D2, which is indeed D1 minus. Ooh, did I mess this up? Yes, I did. I messed this up. You add 1 to get this. This is minus 1. Oh, there you go. That's the benefit of matrices, people. You can see a mess up cohomology computation. You add 1 to get the global section. So yeah, so it's minus 1, which is exactly what we want here. And so you can see this very explicitly here. Now, this actually does have an advantage which you don't get from this, which again, it allows you to be very explicit, which is that you can see here that this is actually an interesting algebra question that you might not have just thought of asking, which is within this vector space, this X vector space, like the actual isomorphism class of the extension itself is going to break this affine space up into a stratification. What is that stratification, and what are those as subvarieties? Using this and using the algorithm, which was actually produced in the proof earlier, you can actually very explicitly construct what these varieties are for each isomorphism class of extension. So the first example, and this is now going to hopefully convince you that my claim earlier about the specialization. The first example is this one. So degree 1, degree -1, this can only have degree 0. Now, this right here is actually a very special piece. It's called the universal extension bundle. Which is to say, this matrix gives us the, for any value of s, gives us the vector bundle in the extension class of x O minus 1. Missing this out, I might be missing this out. Universal quotient, yeah, 1. And there's a nice little, this is my, and again, this is truly my last, maybe, I think this is my last sophisticated matrix computation out there, but I wanted to write it out. Let's keep this here. So this is now a family, right? This is now an A1 family of vector bundles over E1, parameterized by this variable s. So when s equals 0, clearly the vector bundle isomorphism class is OD1 plus is O1 plus O minus 1. Right? I mean, when s is 0, this is already diagonal. If s is not 0, and now I can get out my notes because I did this computation last night to make sure it was correct, and I got it right. Then, so I can just write it down, and this is, if you want to check it, you can do so. Oh my gosh, not a good time to go blurry. All right, here we go. So I'm going to write it out and tell you what it means. So yes, what happens if s is non-zero, then we can take s inverse as a number. And we can note that this only involves t inverses. This side only involves t's. So this is saying that we can actually construct the sort of movement on either side by the necessary matrices of the identity, which means that at t not anywhere, at t being anywhere non-zero, this is actually the trivial vector. So this shows a description very explicitly of this, but firstly, it actually is a bit more. It's the so-called universal extension bundle. This parameter s is precisely the element here that gives us the corresponding vector bundle extension up to Uneta equivalence, I think is the term for these. But in fact, it also shows us the deformation properties of the vector bundles that I was showing, which is that O plus O can sort of be generic and then specialized at a special quotient O1 plus O minus 1. You cannot go the other way, and that's because of semi-continuity. You can't have something that's generically O1 plus O minus 1 and specialize it to OO. That's semi-continuity, although you have to be a little clever about what semi-continuity you use. You can't, the H0s of this are both equal to 2. So what you do is you have to twist this by O minus 1. So that this is H0 minus the H0, 0, and then this one has H0 dimension 1. And you can see these can only jump upwards. So this one has to be the more special of the 2. So there's no way that you can have a family of vector bundles isomorphic generically to parameterized by some scheme isomorphic generically to O1 plus O minus 1 and specialize it to O plus O. That's the wrong way. So I just thought I would mention that as so back now to yes. So yeah, question.
Should that be t to the d2 minus 1 for the vectorial double quotient.
This one right here.
Yes.
So the
Because
D1.
I think you want the dimension. You should have D1 minus D2 minus 1 freedom. And right now you have 2 many.
So it goes from 1 more than D2 to 1 less than D1.
But then won't you have too big of a dimension for the fiber?
I don't think so, right? I mean, 1 minus 1 plus 1. It's possible that I messed it up, but you should be able to kill off at the actual extremal terms. But okay, it's possible. Well, you know, okay, maybe matrices fail too sometimes. Your cohomology can fail and your matrices can fail. So you've experienced both here. So yes, so all right. So the last comment I'll make about this fiber Q, the map of this fiber Q. Last thing I'll mention about the fiber Q, Q inverse of O D2 D1 comma O D2. When D1 is greater, and let's see. D1 is less than D2. In this case, there is only the trivial extension. But there's actually sort of affine space. It's actually going to be of the form as a stack. It's going to be point mod GA to the power of D2. I believe my calculations with D2 minus D1 plus 1. So when they're in the wrong order at the torus, you actually, this is why the stat, you know, here literally the fibers are all just affine spaces. Where's my map from you know, here for T in the correct order, the dominant T base, dominant pair, so D1 greater than or equal to D2. The inverse is just going to be an affine space, but when they're flipped, it's going to be point mod GM. It's sort of almost the opposite order. Point mod GA to the complement, so it's going to be as opposed to AN, as opposed to GA to some power is going to be point divided by GA then. Power, nice. And so there's a kind of seriality. Underlying all of this again is the fact that H0 and H1 never non-zero. So you can never have both ones being non-zero for line map. All right, and then I think the next thing for us to do, yes, okay, this is great. We'll finish in perfect time. Is to look at the fibers of P.
Question you were pointing out the Q is actually smooth. Like it's kind of part of what you're saying here, right? It's like this the relative dimension is actually always the same, which sort of because of Riemann Roch, like even though the H0 and H1 jump around, the Euler characteristic only depends on the degree.
That's an excellent thing. Yeah.
Unlike P, which is not smooth.
Yes, I should have actually. Yes, of course. Q is smooth. Yes, sorry.
Smooth but not representable.
Smooth but not representable. Yes, this is the. So if you're reading Gatesbury and Rodman, they make this. And thank you, Justin. I should have actually made that. You know, skip it over in my notes here. They make this comment exactly that that Q is smooth but not representable, but P has its own problems. P is representative, but it's sort of deadly. It's not proper. And this is why you have so-called Grinfeld concatenation, Lomon concatenation in this whole theory. So this is what we've got to come to with P. So P has its own nice properties, but it's representable in particular. It's a bona fide map of schemes, but it's not the map you want to be able to push things forward, right? You want to be able to use the lower Schmidt functor along P to take an analogy with integration along fibers. And you just can't do that if it's not a proper map, so you need to compact it. So, just ask and go over the other. Yes, thank you so much, Justin. Smoothness is like one of the reasons to bring up that.
Smoothness of the morphism of stacks, right?
Yes, exactly.
So it means that there's a presentation, a smooth thing which is filled in base.
Yes,
And also it means that the whole there's no obstruction to information.
yes. So in this case, it's actually.
But you were saying something different. You're discounting the dimension. What was your argument?
Yeah, I wasn't giving, it was more of a plausibility argument, just saying that the fiber dimension is completely constant.
Yeah, but
So it doesn't prove that it's smooth.
they
That's right, it doesn't prove smooth. So to actually prove the smoothness, I mean, I think what you would do is the fibers are basically some kind of twisted form of BunG in. So it's basically the same calculation that you do to prove smoothness of BunG for any algebraic group, in particular for the input radical. It's some kind of twisted version, right? You have a fixed T bundle and then you, right.
So it's a smooth group scheme N in this case, which is just isomorphic to G.
Basically the same
So
calculation.
That's a good one. Yes, but of course, I mean, the plausibility is basically that the dimensions are equal. The dimensions are all equal because the order characteristic is preserved.
Yeah.
0 minus H1 is always preserved, and they sort of swap their roles in this. Okay, so yes, the last thing we're going to do is we're going to look at this map P. So P is more. So okay, so P we fix a vector bundle E, and we want to know the collection of line subbundles. So it's a kind of sheafy Grassmannian. And so first things first, there is a discrete invariant, which is the degree of L. So let's say that this one again is OD1 plus OD2. And say L is OD. Just keep everything with D's. The map this is slightly overcounting, but the number of maps from this line bundle to this, of course, they don't represent always the same subspace, but it's going to be a GM overcounting, which is corresponding to the automorphisms of this guy here. Should more or less look like the sort of fiber. Again, I'm saying there's a GM overcounting, but there's a little subtlety. And this is what's so interesting. We actually want this not just to be a map of sheaves. We want this to be a map of bundles. So again, Griffin discussed this actually rather opaque, like briefly in the talk. It would have been nice if we had, I don't know, this boring talk before something exciting like the Harder and Riemann filtration in general. But he mentioned how there was a sort of resultant locus that you're excising, and that's exactly what's going to be happening here of bundles. So that is to say, i.e., if i.e. co-kernel of phi can have no torsion. So yes. What does that actually mean? That means that this HOM here, OD to OD1 plus OD2 is equal to the space of polynomials, homogeneous polynomials of degree D1 minus D times homogeneous polynomials in two variables, I could say in two variables. This is P1, project spin R. And notice with this, we do T minus. All right. However, we do not want them to simultaneously vanish. If they have a non-trivial zero in common, then this map will degenerate at that point. It will simply be zero, which means you'll pick up an extra dimension in the co-kernel. And so you would want to cut that out. So there exists this so-called resultant, which is sort of, again, something very classical in Monterey geometry. And so you want this resultant, and this sort of resultant EQ tells us whether it equals zero if and only if there exists a non-trivial common. This is the homogeneous resultant here. So a non-zero root, because everything vanishes at the origin of some means. And so we have to excise that locus. So we basically have this vector space. Let's call this vector space V. We have V. So we have a light here. V minus the resultant EQ is equal to 0, writing these polynomials P and Q, modulo the action of Gn. So these are quasi-projective, right? They're actually affine because you excise a divisor. And in particular, it sort of really wants to be just the projective space associated with it. But it isn't, because you need to make sure that these maps are bundle maps, are bundle maps as opposed to just sheaf maps. And so for this reason, P, the map P, is non-proper. And that's sort of deadly from the perspective of automorphic forms. So one has to compactify. And the obvious way in the case of GL2 is to simply allow this to contain torsion. To simply allow the maps to contain torsion. So that is to say, replace BunB with BunB bar, or as opposed to a line bundle contained in a sub-bundle, a vector bundle where it is locally a direct sum, simply allow it to be a sub-bundle of any type whatsoever. And this, or non-zeros, and a non-zero sub-bundle. And this is the so-called Lomon compactification. In the case of GL2, it also agrees with the Drinfeld compactification. And you can see sort of, again, very explicitly in the case of P1, what all these things mean at the level of varieties. This will suddenly close everything up and turn all the fibers into sort of projective spaces that are glued together. Yes, so this is the beginning of the sort of theory of geometric Eisenstein series and geometric modular forms. So since that's my research, I thought I would give it a little hub. And so finally, what time are we at? 35. Perfect. I will mention the very last theorem. And this will give the sense of BunG. So far we've only dealt with BunGLN P1 and its K points. And I haven't even, and then I've very explicitly drawn out what BunGL2 P1 looks like. But I figure I should just give you the theorem so you see what BunGLN looks like at the level of K points for all. Sorry, BunG looks like BunG P1 for reductive G. For reductive G. So what does this look like? I want to apply just the same analysis. Now, it can't be as detailed. There are things that will go into detail. But the thing that actually does this is Ramanathan's paper. It's called Deformations of Vector Bund. Deformations of G. Here we go. I have the actual title of the paper here. Okay. Deformations of principal bundles on the projective line. And so here is the theorem. So this will give us a very, very complete sense of what sort of the P1 case of the stack BunG X looks like at the level of K points. So there's first the theorem, which is due to Grothendieck-Harder. And so this is an important point to say. The paper, which everyone cites, fiber bundles on the projective line. This is the theorem that paper proves. Like the vector bundles breaking up into line bundles is a 3-page argument en route to proving this. This is a much more interesting, I mean, a much broader result is actually proved in that paper. So this is Grothendieck, and I think according to Ramanathan, the impression I got was that this was only characteristic 0 and Harder gave the arbitrary characteristic case. I'm not sure if that's true. I mean, this one sort of was written, he uses Gaga and was talking about holomorphic bundles. It was not purely algebra geometric, but the arguments were all purely algebra. But I don't know if there was characteristic 0 used at some point, but I haven't really analyzed that. So the first thing is any principal. I need to introduce my terms here, so I'll just quickly use this to describe what it is. So G is a reductive group, and we're going to assume it has a split maximal torus. We're going to assume that it has the standard root data, so the characters of T, the roots, the co-characters of T, the co-roots. And I think we may assume some kind of choice of positive roots. Because I think it's called a base root system. We have this. So any principal G-torsor on P1 admits a reduction of the structure group to T, unique up to Weil group. Action. Okay. So regarding this root data, this is something that Professor Drinfeld, when I was a very first year grad student, told me caused him angst in his life, which is amazing. I mean, I was fascinated to hear this, that he said that this caused him a great deal of confusion. He said there are two cones in Lie theory. He said he didn't realize the difference between these two cones. And he says you need to learn your two cones early, and that way you'll not have the same confusion I did, because my early research was all in GL2 and the two cones make absolutely no difference. And these are the cone of fundamental weights versus the cone of dominant, positive weights versus the cone of dominant weights. And so just briefly, I'm going to take a tiny interlude. The critical point he insists is that positive weights have a conical angle that's bigger than 90 degrees. And the positive and the dominant, so this is positive. These are positive. There are positive roots and positive co-roots, positive weights, positive co-weights, but this is the positive cone, or whatever lattice you're in. And if your dominant always greater than 90 degrees, and your dominant cone has angle less than 90 degrees. All right. So that said, on the dominant cone of weights, or a dominant co-character, say in this case, there is an order, and it's given by the positive cone. So you think of translating this cone up through this narrow cone, that gives the order. So like this one is certainly less than anything in here, but you're only really assessing it in this cone. So this is the important point regarding order of roots and co-roots. So there's these two cones, the positive and the dominant. The data are going to be classified by the dominant, but the dominant are ordered by whether their difference lies in the positive. So I think drawing the picture probably does better than belaboring the point. Ramanathan spends about the first 6 pages of his paper just going over the basic sort of structure theory of Lie groups of algebraic groups. And so I wanted to mention this before I state the theorem. So it is the dominant cone that is acted on by the vial chain, looks like a vial chain. He said also, Professor Trimble also told us this rather fun story that apparently Selberg, this is something he heard from Bernstein, that Selberg, this is math goss, you'll need to tell me if it's correct, Professor Weasley. Apparently Selberg had tried to do a whole bunch of work in Eisenstein's series, and he sort of found her on exactly the confusion of the cones, 2 cones, according to Bernstein, who then transmitted this to Grinfeld, and then transmitted it to me now. So this is kind of a fun little bit of, oh gosh, I'm being recorded. Okay, well, yeah. So this is so always know your 2 cones. So yes, so in particular, P1 is a GM torsor. Oh, always. P1 is a GM torsor. P1 lives under A2 as a GM torsor. I have to minus the origin, thank you. That's something not right there. GM torsor. And now you can consider the associated bundles. If GM maps to the subset of G is a dominant co-character, let's call this what's a good letter? Maybe mu, lambda. Then you can always just take the associated bundles. So it's the A2 minus the origin times lambda G. So this changes it from a GM bundle to a G bundle. And this gives you a set of all such things. Each lambda is the collection of all G-torsors. Collection of all G-torsors over P1 for lambda, the dominant co-character. So that is the substance of the Grothendieck-Harder theorem, that you can obtain everything from this sort of fiber change from the associated bundles of the canonical GM torsor of A2 minus 0. And this gives you all the different G-torsors for any reductive G. Ramanathan's upgrade of this is to say which ones sort of lie in the closures of which ones. And that will be the last thing that we talk about before I let the people go. So that you can again see what the stack will sort of look like. Called this torsor E sub lambda. We say we have, which again is an element of BunG G E1K. we have that the point E mu is in the closure of the point E lambda in this stack, if and only if mu is bigger than lambda. I.e. mu minus lambda is in the positive cone. So altogether, what do we have? The points are characterized by lattice points inside a cone. The specializations look like the specializations of this wider cone, going sort of deeper into the cone. And Ramanathan also characterized the automorphisms of such K points. But this is what BunG of P1 for general reductive G looks like. And strangely enough, some of the arguments, when you look at them, if you sort of compare them, again, a perfect talk in which I had an extra 30 minutes to go through Grothendieck and compare it would have made this really clear. Actually, that you can see how all these arguments are sort of in the shadow of Grothendieck's original argument, breaking up a general vector bundle into a sum of line bundles. And so most of the arguments of this kind go through the sort of, again, the SO2 triple work to show that certain maximality conditions are satisfied. Everything you see all sort of line up again in the general argument that he gives. And again, also I should mention the other critical ingredient to this argument is he shows first B reduction, the theory of B reduction to Borel, and then T reduction from that. And of course, B reduction is something we've now discussed, at least in the case of GL2, so you have a feeling of what it should look like. So my hope with all of this, annoying finagling and computation, is that I can at least give you a sense of a concrete picture of what BunGL2, what BunG of the curve, in this case P1, looks like and sort of feels like. A more interesting case would be the elliptic curve, because then pick is non-trivial. It looks like the elliptic curve. And so the points get sort of, the points in each vibration get blown up into elliptic curves and they become much more interesting. But with this, I think I will conclude and let the people go. Thank you so much. It's been a wonderful quarter.
Say something about what you're doing next quarter.
Yes, so this is a good thing while we're still recording. Next quarter, it's going to be, all right, this is, I have to give credit where it's due. This is Nikolai's pun, not mine. It's not going to be the BunG seminar anymore. It's going to be the BunG seminar. This must be quite extraordinary for Professor Yazzie, saying how incredibly untechnical this talk was. You should have seen the previous three. And you're going to wait until Sasha's comes in. But we're going to be talking about D modules on BunG, and our hope is eventually to prove. So this quarter we proved, I think it was talk 4, or we gave an outline of the proof. It was Ginsburg's talk. We proved that BunG is good. Okay. So that's a fine start. But next quarter we're going to prove something much better, which is that BunG is miraculous. And so we're going to be working up towards the theorem of miraculous duality. And so we have, and we're very glad to include Justin here as our co-organizer and assistant in this process, because at this point it becomes rapidly on the cusp of what we're sort of capable of actually, just between Nikolai and me understanding here. So it's going to be very good fun. And the first talk will be March 22nd. It'll be on the truncatedness. So part of this will be the compact generation of D modules on BunG. And within that, there's a geometric property, not too much far from along the lines of this, which is this truncatedness, how to build up BunG. And Sasha is going to discuss that in great detail. So that's going to be the first on March 22nd. We're still lining up speakers for other talks. You may hear from us. And again, so please stay tuned for next quarter. It's going to be very exciting, and we'll upgrade from the to D and from good to miraculous. So thanks so much.
Story